I'm a bit of an outsider here. I wasn't really sure what I was coming into, and therefore I wasn't really sure what it is that I should try to say. But following the discussion of yesterday, I think that my main message is going to be something like, there is no code. Or perhaps even one of the most paradigmatic examples of code, which is symbolic algebra, is not really a code, not in a strict computational informatics sense. So maybe this is what I'm trying to say, and you'll tell me at the end whether I did say that and whether I was convincing. Okay, so I'm going to talk about the emergence of symbolic algebra between the 14th and 17th century in early modern Europe, in late Renaissance Europe. And I'm going to present this story from 2 points of view. One of them is a scholarly point of view, which you have in this left-hand side. So people in France, England, Netherlands in the 16th and 17th century, people who supported themselves by using their family property or public positions or university position, who wrote in Latin and vernacular. This is going to be one part of the story, the shorter part of the story. I'm just going to be very brief about it. Then the main part of the story is going to be what happened in Italy between 14th and 16th century, what we call the Abbacus culture. So this is about people who were teaching mathematics to children of merchants, so practical, economical mathematics. And they were also doing things like accounting or surveying or measuring or engineering, etc., or architecture, some of them. And they wrote mostly in their vernacular. So we're going to start with the scholarly side of the story. And in order to get into the scholarly side of the story, we need to understand the heritage which these people get. And this heritage is about many different kinds or many different natures, many different species of magnitudes. So obviously there are the numbers which are based on the unit. The unit itself is not a number, but there's a bit of a technicality. A number is a multiplicity of units, so 2 units, 3 units, etc. Discrete collections of an indivisible unit. But then you also sometimes need fractions. So there's a problem thinking about the fraction as a division of a unit which is supposed to be indivisible. So one of the solutions is to think in terms of relative units, not an absolute unit. And this unit may be called 1, and this other unit may be called 1/3. And then you take multiplicities of these relative units in order to generate fractions. The next kind of magnitude is geometric. So lines of certain length or shapes of certain areas. And this is something very different than the numbers and the fractions. It's not something that's translatable to each other, because one is continuous and the other is discrete. So you have to be careful not to confuse them. In order to relate those different kinds of magnitude, the continuous and the discrete, you need something called ratios. Now, from our point of view, it's very difficult to understand that there is a difference between a ratio and a fraction, but there is actually. A ratio is a relation between 2 magnitudes. So you might have a situation where the ratio between this square and that square is as the ratio between the number 3 and the number 2. But neither of these ratio is the fraction 3/2 or something like that. So the concept of ratio can give you something that relates the relation of these 2 squares and the relations of these 2 numbers. But it's not quite a fraction. Now, perhaps by the time our story starts, the difference between ratio and fraction is not so pronounced anymore, and there is already some leeway moving between them not very carefully. Next is roots, irrational roots. So if you have a square of size 2, or more precisely a square whose ratio to another square is 2:1, then the side may be expressed by something like square root of 2. This is not expressible by a fraction. This is an irrational number, so it poses some kind of challenges, whether you think about it as a number or only as a continuous magnitude. There's some delicate points and difficulties here. And then this gets even more complicated when you get binomials, which are combinations of integer and irrational numbers. Gets even more complicated when you get to algebra, which emerges in Europe at this period after it's being imported from an Arabic context, where you have the signs for the unknown, for the square, for the cube. I'm using here the, oh, you don't see it. I'm using here the, the modern signs and the indigenous Italian signs. The problem with the algebraic unknowns is that they may represent numbers or may represent other kinds of magnitudes, and things start to get shaky. But one of the projects of early symbolic algebra is precisely to get over these differences, to be able to talk algebraically about all kinds of magnitudes together, because algebra can speak about different kinds of magnitude. And then there's a theoretical challenge about how to do that. And there's a very nice classical analysis by Jakob Klein, who gave a review of the different attempts to overcome the problems of distinguishing between different kinds of magnitudes. And I'm going to go over it very, very briefly with no detail, just to give some sort of counterpoint to what I'm going to say later. So one suggestion is to hypothesize a sort of genus that supervenes the number and the geometric magnitudes and other magnitudes, and somehow explore mathematics at the level of this higher genus of quantity or magnitude. Or stop thinking about 1 as the principle of number and start thinking about 0, the decimal 0, as the principle of number, in analogy perhaps to the point being the principle of lines and geometric magnitudes. So another way to rephrase or undo the difference between numbers and geometric magnitudes, or saying that we are trying to abstract the notion of magnitude, which is beyond sensibility, but we can't do it unless we have an imaginary object to work on, but the imaginary object can be a symbol. So perhaps this is a mathematics of symbols rather than sensible magnitudes. And another attempt, which is about rephrasing the notion of ratio in order that it subsumes all kinds of other numbers. Every number can be maybe thought of as a ratio, and then everything is homogeneous because it's all ratios. So this is the theoretical approach. And this is the end of what I want to say about that, and I want to move on to the other approach, which is, let's call it the practical approach. The approach adopted by these Abbacus masters, these teachers of mathematics to children of merchants. And they also encountered this issue of different kinds of magnitudes as part of their heritage. But for them, the issue was not so much the different theoretical definitions of what each kind of magnitude might be, but the fact that there are different rules that apply to different kinds of magnitudes. So when you multiply numbers, you learn this multiplication algorithm. But when you multiply fraction, you need to learn that you multiply numerators and denominators and divide the results. And there are different practices when it comes to geometrical magnitudes and roots and binomials and algebraic terms. For instance, the unknown times the square equals the cube. So the difference is really a difference of rules, of practices, and perhaps less a theoretical difference, which was less important to them. And the story that I'm going to try to tell now is the story of how the practices of these mathematicians, of these teachers, helped undo the difference between different kinds of magnitudes. So they're not going to supply a theoretical explanation. They're just doing things which are in their background, in their practical background, and which end up changing the notion of magnitude. And the first element that we need to consider is the effect of economic conversion. So these are people who, as I said, teach children of merchants. They teach in an economic situation, and therefore there's a lot of economical discussion in these textbooks, in these manuscripts that they write. And you can find paragraphs such as the following. The grossone, which is a kind of coin, is worth 20 quattrini. But at present, it goes for 21. There was a little bit of inflation or change of the value of the metal or whatever. And while the fiorino, to this money, there's no fixed value because sometimes it goes up by a few scudi and sometimes it goes down. There's this exchange rate fluctuation. There is an imaginary value, imaginary in the sense that there is no real coin of that value. There's an imaginary value that's called golden scudo, which is always stable, so that the fiorino is worth 20 golden scudi and the golden scudo 12 golden denari. The point of this imaginary value is for bookkeeping. Many of them were bookkeepers, so you have this technique of a stable bookkeeping conversion that does not relate to any real coins. The point of this paragraph is to show that within this, Maestro Benedetto is 15th century Florence, but you see similar paragraphs in many other textbooks. The point of this paragraph is that values in this culture are something that is convertible and unstable and changing and can even be imaginary, already before you have any algebra or something like that. And this is also an economic reality where everything is convertible to money. Land is convertible to money. Commodities, of course, are convertible to money. Labor is convertible to money. Time is convertible to money by means of interest rates. So things move and change their value and their nature, which weakens the attempt to distinguish different kinds of magnitudes. The next component is the arithmetic conversion. The conversion that comes in the context of doing arithmetical operations. For instance, when you do additional fractions. So you think about the quarter as one kind of relative unit and the sixth as another kind of relative unit, but if you want to sum them together, if you want to have a bottom line which you can understand, then you need to convert them to a common unit, which is the common denominator here, the 12th. So you have, in order to do arithmetic, you have to change the nature, the kind, the species of the magnitudes you're working with. And people sometimes get so used to it that they do it even when it's not really necessary. For instance, in multiplication, there's no point in doing common denominator, but sometimes they do. Another example is when you multiply a number and a root, you don't want to work with different kinds of unity. Like when you do bookkeeping, you don't want to have the bottom line a combination of pounds and euros. You want something that you can understand in terms of one unit. So you have to put them together, homogenize them. You have to turn the 2 into square root of 4 in order to get the result square root of 12. And again, this kind of weakens the assumption that numbers and roots are something very different. The next practice that has to do with changing with weakening the distinction between kinds of magnitudes is what I called here recreational nonsense. I mean the fact that when you do a textbook solution, you're not committed to any practical constraints. So things that you can't do in the real world can be done on paper. For example, in this problem, there's an area of land and you want to build houses on it, and the total area is going to be this number, and the area of a house is going to be this number, and when you divide, you get 228 houses and some fraction of a house, which obviously doesn't make sense in any architectural context. Also note that there's no space between those houses, which is rather uncomfortable. But this is the kind of thing that you can do on paper, which weakens this distinction between an indivisible unit, like a house, and fractions that are supposed to have different meanings. Or another nice example. In this example, two people give each other partial information in order to figure out how much money each of them has, and one of them says, well, if you give me the root of your money, I would have 30 units of money. But what is the root of money? I mean, the root of an area is the side of the square, but what is the root of money? Especially when the solution here is irrational. So it actually has to give him an irrational amount of money, which makes absolutely no sense. So again, a distinction between continuous and discrete, which is necessary in the context of real money, disappears because we're doing calculation on paper. The next is perhaps my favorite example in the entire history of mathematics. I think that anybody who heard me speak probably heard this example as well. And this is the following. If 4 were half of 12, what would be 1/3 of 15? And this sounds kind of stupid because 4 is not half of 12, 6 is half of 12. What do you mean if 4 were half of 12? And of course, you need to read it in context. Look what's comes before it, what comes after it. And you see that this comes in the context of conversions. So you can make sense of it by saying maybe if 4 pieces of bread were worth half of 12 fiorini, or maybe if 4 fiorini were worth last year, what half of 12 fiorini are worth today. And then this question gets some sort of sense. But the point is, what's really important for me here is the fact that the sign, the numerical sign, this 4, does not necessarily represent its face value. It may represent another value. Here it represents the value 6. So when you look at the sign, the relation between the sign of the value is not fixed even before you go into all sorts of economic conversion and instabilities. So the sign which can change its value might end up changing its nature as well. And this is already part of the practice of these people before you start getting into higher algebra. Note also that units are often omitted or implicit in practice. So when I'm talking about 4 pieces of bread, I won't write pieces of bread after every time I write a number, because you know I'm talking about pieces of bread. So this omission of the nature of the number, of what it counts, of the nature of the unit, is again part of the practice, and it allows to forget what a number should mean and contributes to these changes of value convertibility of nature, which weakens this distinction between different kinds of magnitudes. The next example is another kind of example where signs do not represent the face value, but this is a little different. Here, we're talking about questions where the approach is to suggest or guess a certain solution, which you expect not to be correct, and then see what happens with it and correct it accordingly. So here the question is to find 2 numbers in ratio of 1 to 2, such that the sum of the square of the numbers is 49. And the solution goes like this. Well, first, just guess, take, imagine, start working with 1 and 2, because the ratio is 1 to 2. So the ratio is okay, but the square of the sums is 5, not the 49 that you want. So you need to fix it. You need to rescale everything, multiply the result by 49 divided by 5. And because these are square, when you rescale everything by this factor, you rescale each term by the root, and you get the required solution. Now, my point here is that these numbers, this 1 and 2, do not represent the values 1 and 2. This is not their function here. The function here is to be place value for the placeholder, for the correct solutions which will come later. I don't expect them to represent these value. I represent them to end up being these value before I have any sign of variable or symbolic algebra, or at least in parallel or as an alternative technique. And this related to another practice which is not simplifying calculations. For example, I have this problem and my solution ends up being something like 5 times square of 3 plus 3. And instead of simplifying it, calculating what is 5 times square of 3 plus 3, I leave it as it is in my calculation, in my account, because it tells me something about the form, the general form of the solution, 5 times something square plus the something. So, because when I'm solving problems, I usually want to represent a technique, something more general rather than the specific value I'm working with. And here is a very nice example, and this comes from a later author from Bombelli, middle of 16th century. The problem here is to figure out the binomial coefficient. It's not really important to understand a lot what it is, but when you take a sum, a binomial, and raise it to a certain power, then it breaks down to a sum, and Bombelli is interested in explaining to us how you find these coefficients. And in order to do that, he takes what seems like a concrete example. He takes 30 for x and 2 for y, and he just multiplies 32 by itself 5 times. But if you just multiply 32 by itself plus 5 times, then you won't break the result into these components and you won't get anything. So what he does is separates different components with different powers of 30 and 2, and then gets these 6 components which correspond to these 6 components. And then you can extract the coefficients. But again, the number 30 or the number 2 here do not represent a face value. They represent something else. They represent a sort of general quantity. And if you're not convinced, then see what happens when we move from Bombelli's manuscript to Bombelli's print edition. He's actually replacing the number 30 by this sign, which is his print sign for the unknown. So this number 30 does not represent a numerical value. It represents an algebraic entity or a formal entity. So again, a number or a sign does not represent, it's not only that it does not represent its own face value, it might be there not to represent any value or to represent a general value. And this is even accentuated in the following examples when we are dealing with signs which have no value at all. So this is the problem. You have an equation, the equation of the third degree, and you want to solve it. And the common technique at the time to solve this kind of equations is to do what we call today a change of variable. Again, it's not important to understand what it is, but after you do the change of variable, you get a simplified equation, an auxiliary equation. And by solving the auxiliary equation, you can figure out the solution of the original equation. So Bombelli says, having found the value of the tanto, the unknown of the auxiliary equation, having solved the original equation, if you add 3 to the solution here, then you get the sum would be the value of the tanto, the solution of the original equation. So take the solution, add 3, and get the solution here. But then he adds if one could. And he adds if one could because one can't. There is no solution for this equation, at least not a positive solution, which is what he's interested in. So basically he's saying the non-existing solution of this equation, if you add 3, you get the non-existing solution of that equation. So he's working with signs that represent values that he knows does not exist. And how can we make sense of that? We can make sense of that because, again, we're not talking specifically about this or this equation. We're talking about the general technique, and these coefficients, these numbers, do not represent only their face value. They represent general parameters, and he's displaying a method that will work in a general case, and therefore he doesn't mind saying that this non-existing solution, if you add something, you get this other non-existing thing. And what I want to do next is maybe explain how these practices contribute to the emergence of new mathematical entities, new algebraic entities, of new numerical entities. And I'm going to start with the last one, with the most advanced one, or the most recent one at least, which is complex numbers. And the story here is rather similar to the previous story in some sense. You have this equation of the third degree, and you want to solve it. And again, there's already a method for solving this kind of equation, so it's just using this method. And when you use this method, this is what you get. You just plug in the parameters into the formula, and this is what you get. Now, every other mathematician up to that time using this formula would simply throw it away, because what is the square root of minus 121? There is no such thing as a square root of a negative number. But then Bombelli says, well, yeah, I'm already used, well, he doesn't say it explicitly, it's my reconstruction. I'm already used to working with signs that represent non-existent or shifting or other values, so why not continue doing it here? I know how to take a cubic root of a binomial, of a sum of a number and a root. So let's just use my technique for taking the cubic root of a binomial, and by using this technique, I get this. And then the square root of minus 1 here, it cancels out with the minus square root of minus 1 here, and you get 2 plus 2 equals 4. And if you plug in this 4 into this equation, you get the correct result. This move is explicitly called by Bombelli sophistic, if we're talking about here about sophistication. So this is explicitly pronounced as a sophistic approach to the problem by Bombelli. But the point is, again, in a culture where you're so used to work with signs which have convertible values and convertible natures, and they are separated from practical application that might constrain them, and they may carry values other than their face values, or they may carry general values, or they may carry no value. If you already have these practices in your arsenal, then it's perhaps not surprising to find the use of roots of negative number done by people in this culture. So after all these practices have already shaken up your distinction, your attempt to distinguish between different kinds of magnitudes, then working with these new magnitudes is perhaps something not very scary or not very surprising. The next piece of the story is about the emergence of algebraic symbols and negative numbers, and I'll start with algebraic symbols. You see here a piece of a manuscript by Maestro Benedetto, the same one from the slide that Giuseppe asked about, so 15th century Florence. On the right, you see here the running text, and on the left here, you see the draft calculation. This is very rare. Usually we see this, the running text, but people throw away the draft calculation, so it's very nice to have them both. This is a story about 5 people who go on the road and find a purse. And the first person says, well, if you give me the money in the purse, then together with the money in the purse and my money, I will have 2.5 times as much as the rest of you. Then the second says, well, if you give me the money in the purse, then together with the purse, I'll have 3 1/3 times as much money as the rest of you. The next says, I'll have 4 1/4 times as much money as the rest of you, and et cetera, et cetera. This problem gives us a nice key, a nice approach to these two problems of the emergence of the algebraic sign and the emergence of negative numbers. So first, the algebraic sign. Look, for example, at this part of the running text, the full text. It says 1 quantita and a half. Quantita is the amount of money of the first person in the story, so how much money he has before he gets the purse. So 1 quantita and a half and 1 borsa and a half. Borsa is the amount of money in the purse. 1 quantita and a half and 1 borsa and a half, men or less, 5 fiorini. This ligature represents the currency fiorini. So just nothing here except writing some quantities. It gets more interesting when we look at the draft calculations, and then you see this ligature qua, which is the beginning of quantità, and the letter B, which is the first letter of borsa. Now, the fact that algebraic unknown signs historically come from shortening longer words, this is not big news, this is trivial and well known. But what is interesting here is that when you start working with these letter symbols for quantities, this ligature or this letter to represent quantities, you are actually not inventing a new technique. It's already there. Where is it already there? Here. You already use ligatures or letters to represent quantities. You don't need to invent a new technique. The technique is already there, working with this ligature to represent quantities, and you do similar things. Also, the whole algebraic approach, the whole algebraic analysis, is very closely related to bookkeeping, the double entry bookkeeping, which is developed at the same time, at the same place, by the same people, balancing columns of quantities in order to do accounts. They're doing similar stuff here. So you're basically importing the practice from existing economical practice into this newer algebraic analysis using symbolic letters, and it's not something completely original for this culture. It already comes into play in Arabic mathematics, but I won't have time to get into that. Just to mention that this is not something just emerged independently without any background by the geniuses of Europe. This has a long world history. Next, I'm going to talk about negative numbers, and again, we're looking at the same problem, but eventually when we look at the bottom line equation, the last equation that you get a certain equation that looks like this. So and so much times B, the borsa, the money in the purse, plus so and so much qua the quantity, the amount of money of the first person, equals 0. This is a problematic equation. It's a problematic equation because if you actually have money in the purse and this person actually has money, then the sum can't be 0. So how can you make sense of this? So this problem has a long history, and one of the people who dealt with it was Leonardo Fibonacci, about 200-300 years before Benedetto. When he encountered that, he said something like, well, this makes no sense, so we have to rephrase the problem. What the first person has is not a quantity, is not money, it's a debt. And if you take a person with a debt, say he owes 2 fiorini, and he finds a person with 10 fiorini, then altogether he has 10 minus 2, he has 8 fiorini as his property. And so you rephrase the entire problem according to this, and you get so and so many B less so and so many Q equals 0, and then you can calculate the debt of the first person from the Borsa. You have to rephrase the whole problem in order to avoid negativity. But by the time this problem reaches Benedetto, he does something else. He says, well, just solve this equation by saying that the amount of money here is this amount of money divided by the coefficient debita, which can be translated as subtracted or as debt. So what happened in this time between Fibonacci and Benedetto? What's the change of approach that allows him to do something that looks much more like saying, well, if B is positive, then Q is negative. If B is credit, then Q is debit. Well, in between Fibonacci and Benedetto, we have this, one of the many treatises we have is Dardy's algebra. And in Dardy's algebra, this is a very long and tedious treatise about many different kind of equations and how to solve each equation. Then at the end, there are sort of endnotes, probably added by some copyists. The first endnote deals with this equation. 5x plus 5 times the unknown. Of course, I'm not using original notation. This is a modern notation for his older formulation. 5 times the unknown plus square root of 6 equals 13. One of the things that people tended to use at the time, again, because of this tendency to homogenize it, because we need to turn everything to the same kind of magnitude to do arithmetic, is kind of square everything to get rid of the square root of 6. But this guy says, well, we can do something simpler. You can just subtract the square root of 6 from both sides, and then here you get a binomial, numberless root, and you know how to work with a binomial. You can divide the binomial by 5 and get the result. And then, without any comment, without any special introduction, without saying, look, this is the first time this is happening in a European manuscript, which as far as I know it is, he presents this equation. And he says, well, how to solve it? How to solve 5 times an unknown plus 15 equals 0? Well, just subtract the 15, move it to the other side. You get here this kind of binomial where this is a strange binomial because it begins with a 0, but it's still a binomial. So let's just divide by 5, and you get the result 3 debita, 3 as debt or 3 subtracted. The actual explanation is this. In some equations, you can run into this kind of, in some kind of problems, you can run into this kind of equations. As we saw in Benedetto's case, you start with a normal sounding problem and you run into this kind of equation. And then what you can do is subtract the number from both sides. You get nothing less number, which is presented like a binomial, divide by the coefficient, and what you get will be the unknown debita. So again, what you see here is that a certain practice already leads you in a certain direction, not a theorizing, not a conceptual analysis, but this strange combination between the formal analogy of this term to a binomial and substantial or conceptual interpretation of the homogeneity between money and debt, which is very, of course, common at the time. And this serves as the components which allow you to create new mathematical entities like the negative numbers that will emerge from this kind of notations. So altogether, what I was trying to tell is a story where the differences between different kind of magnitudes are challenged or questioned, well, not explicitly questioned, but practically undone by various practices that already exist in a certain economical, practical environment. And because of this weakening of the differences between the different kind of magnitudes, these practices move on to generate new mathematical entities like complex and negative numbers and symbolic unknowns. And perhaps my point here is to say that if you look at the emergence of symbolic algebra, what you see is not a code. What you see is this conflation of many different practices, this different level of conceptualization and practice, which combine together in perhaps unexpected way, unforeseen way, to create something new. And perhaps this is a good way to think about codes even today. Codes are never really strictly codes. Codes are what we call a code is a combination of various layers of practices, various layers of conceptualization that are not really separate, that are not really separable in practice, that run against each other, that combine with each other, that collide with each other to create new meanings, new practices, new science. So this is perhaps the lesson that we can take from this late medieval, early modern story. Thank you very much.